Bangladesh, I guess, heavily going towards the semiconductor industry, semiconductor workforce, and how that will be developed. I am an academic. I work in a university, so I know nothing about it. So what I'm going to talk about, and what I can talk about mostly, is about academic stuff. So that's what I'm going to focus on. But over the last 5-6 years, I have also been participating in some of the US semiconductor initiative at various roles. So I have some experience that I can draw upon, and I can share that. But my talk, my presentation is mostly going to be academic, and because of that, I also promise that there will be equations in my slides. All right. So so what I'm going to talk about is mostly some of the stuff that we are doing in our group, which is to look for new opportunities for energy efficiency in AI hardware. And I'll give some background to why we are looking into this. So, of course, AI has taken our world by storm. Whatever we do today, we think about AI, but it does not come for free. AI is taking a lot of energy. In fact, if you look into this, you will hear that big hyperscalers like Microsoft, like Google, they are thinking about going after nuclear power stations just to run their data centers. Okay, so this is we have talked about, somebody like me, my entire career I'm talking about energy efficiency in electronics. 17 years ago, we used to show projection that, hey, this is going to become unsustainable, but it does not get traction as much as how it is today, because now it is really becoming unsustainable. And I'll give you an example for that. So this is the data plotted for the power taken by a GPU board by NVIDIA over the last 5 years. So 2020 there was Tesla GPU. Today we are doing the Blackwell GPU, and you can the Blackwell 200 is the benchmark chip. GB200 is a special chip. The board has 2 Tesla GPUs. But if you actually look at the power dissipation, you can see that the one board, B200, takes around 1 kilowatt, just one board, okay? And that power has gone up 5x over the last 5 years. Okay, so power rating of these GPU boards that we use for AI calculations is going up by 4 to 10x in the last 5 years. Now, let's look at, often the money number actually gives us a real feeling of what it is. In 2023, this is based on publicly available data. In 2023, Google's data centers consume 24 terawatt hour of energy. So 24 terawatt hour, I'm sure that Google has a way to buy electricity cheaply. But if you actually look at a standard electricity bill in the US, 24 terawatt hours comes out to be $6.5 billion of electricity bill. That's just for one hyperscaler over 1 year. Okay, so now if you assume that energy dissipation is going up 4 to 10x every 5 years, that essentially means that energy dissipation in an optimistic sense is supposed to go up by like 20 to 50x in 25 years. That's optimistic because I'm taking a linear projection. If you take a geometric projection, which is actually more realistic, it will be going up by 100 to 150x. That essentially means that electricity bill for one hyperscaler over 1 year is going to be $130 to $300 billion. Now our industry makes a lot of money, no question. It's over the entire semiconductor ecosystem is closing on to $1 trillion a year, which is 1% of GDP. However, this number, whoever you talk to, is not sustainable. So we are starting to get to a situation where just power dissipation is going to stop what we are doing. And overall, so far, our data center providers have hidden it well. We don't really, when we use our, let's say, ChatGPT search, we don't think about how much power we are spending. But this will come in. The first time, the rank and file population understood what power dissipation means is by crypto mining. A few years ago in the US, even my grad students were setting up servers to do Bitcoin mining. They cannot do it anymore because the electricity bill has become more expensive than what you can do by just doing like personal level Bitcoin mining. The industries who do Bitcoin mining in a scaled manner still can do it, but personal level we cannot do it anymore. It's just not possible because of the power dissipation. And the point that I wanted to make is that we talk about AI, we know that AI is going to do this, do that, and many things. However, we are coming to a situation where power dissipation is going to stop us from doing all the things that we do, which is a problem. Even, and at least in the US sense, they talk about national security problem, which basically means that you would like to have access to extreme amount of energy. You have to be able to generate a lot of energy. Whoever has access to energy generation will be able to run more and more AI. They will become more and more efficient. It's a runaway train. So something has to be done, right? This is, for a country like Bangladesh, this may become, again, a problem like oil. If you need gas to run everything and you cannot generate gas by yourselves, then how do you handle that? So, those are very, those goes into regimes that are not my expertise. I am a university professor again, and I think about what can we do fundamentally to address this problem. So if you think about a microchip, if you think about today's processors, everything is built on transistors. Again, we were talking about NVIDIA GPU B200. That uses 207 billion transistors on one chip. Again, just think about the number, 207 billion. That is 1E11 components on a single chip. Okay, so this is a marvel of human discovery, that one chip can have so many components and we can actually make them work. Now, the thing is that because the basic building block is the transistor, all your power dissipation essentially comes from whatever you dissipate on that transistor. And the transistor, through the work of thousands of engineers over many years, what we have been able to do is we have been able to keep it as a very simple device. If you think about a transistor, it is just resistors or capacitors, and basically the power dissipation is CV squared. The capacitance of the transistor times the voltage that you run. And over the years, the voltage was coming down as we were going down to smaller and smaller devices. But what this plot shows is that has essentially saturated out. Today, we are around 700 millivolt. If you look at the most advanced nodes, they're saying maybe we'll go to 650 millivolt. But that's it. This is where it is saturating out, which means fundamentally, we are running out of opportunities to reduce energy. The other thing that has become a significant problem, especially for AI workloads, is that we need a lot of memory. The memory is off chip. All your DRAMs are sitting on the board that is off chip. So as you try to access that memory, you have to send and receive data. That communication spends a lot of energy. And the more memory I need, the more communication I need, I spend a lot of energy. So, again, if you are a techie, you look at a AI server today, you look at the, water dropped from. I want to just make sure. Yeah, if you are looking at a DRAM access, your main memory access, that's 50 picojoule per bit, which is a lot of picojoule, because if you think about, you are working at the high bandwidth memories full bandwidth that they provide us today, over a terabits per second, that becomes already 100 watt. So your memory module itself can be 100 watt. And so then your processor does not have any power. If you buy a desktop or a laptop, you will look at the power converter, it can only give you something around 70 to 90 watts. So power dissipation is cropping up everywhere. So this is where things are. And again, I'm at a university. We look at what can we do. So if I had to set up 3 challenges for universities to look into fundamental stuff, this is the number 1 would be running devices at a smaller and smaller energy or voltage. Going to smaller and smaller devices has always been the driver for the industry, and access to more and more memory. Right now we cannot do it because we are getting stuck by the power dissipation. If you talk to today's memory designers or memory vendors, if you talk to Micron, Samsung, SK Hynix, they can in principle provide a larger bandwidth, but they cannot handle the power. Because again, you need 50 picojoule per bit. Okay, so what can we do? So one of the things that we have been doing since the beginning of my career itself is we ask the question that can you fundamentally reduce voltage in the transistors? And for that you have to change the way transistors work, because if you do not change the way transistors work, the industry, it's a $1 trillion industry, it knows what is the limit. It can work at that limit, and that's what it has been doing. So one of the things that we said, that transistors are what we call the field effect device. We apply a voltage, it creates an electric field, and with that we turn on or off the switch. So can we change the field effect itself? Because that is the fundamental process. And the way we create a field is that we put a voltage through an insulator. So the insulators, we know them very well. Any glass that you're using on your watch or something else, that's an insulator. Electricity does not go through it, but you can apply voltage and you can get an electric field going through it. So what we said, that we can, in principle, look at a slightly different insulator, which is often called a ferroelectric material. And why we did that, I'm not going to get into the details of it. I was just having discussions with Professor Rizwan Khan about second law of thermodynamics. It actually comes from, the motivation comes from the second law of thermodynamics, because in a ferroelectric material you have electric dipoles which are ordered, and the reduced order gives you reduced entropy, so you can get some extra energy out of it. But not going into that details, what I'm going to mention is that you have an insulator which is called a ferroelectric. This is found in nature, but what it has is it has dipoles inside it, and dipoles have electric fields. So these are materials where even without applying an external voltage, you can have electric fields inside. Any fields is also associated with energy, so these materials actually store energy. So this happens when the material goes through a phase transition, and it is able to store that energy. And so when we look at the internal energy of this material, it looks like this W. I don't know if my cursor is viewable here, but if you look at the rightmost plot, that shows the energy landscape of this material, and it looks like a W, and that a little bit of a hump in the middle, that is reminiscent of the stored energy in the material. Okay, so by this stored energy, it is distinguished from a regular insulator like glass. It has stored energy in the material. So if we look at that stored energy region, again, I know that many of you are here electrical engineers, and I promise that I'm going to use equations. So here is an equation for you. When we look at the energy of an insulator, it is charge squared divided by 2 times the capacitance, Q square over twice C. But you look at that middle region, the curvature is negative, which means it has to be Q square over 2 times negative C. There's no other way of doing it. Q squared is always positive. So that gives us a region where the capacitance is negative. So that's what I said, that this is a negative capacitance material, and we are going to use it. How are we going to use it? So if we put a negative capacitance with a positive capacitance in a series combination, the total capacitance actually goes up rather than going down. The textbook tells us that if you put 2 capacitors in series, the capacitance must go down. It is smaller than either of the 2. That's what we learned in our first year, right? But this goes in the other direction of what the textbook says. You put a negative capacitance with a positive capacitance, the total capacitance goes up. Now, if you think about it, capacitance is dq dV. So how much charge can I switch for a given change in voltage? So if the capacitance goes up, I can switch the same amount of charge at a smaller voltage, and that allows me to reduce how much charge I have to change in my transistors in a non-conventional way. This is something that is not possible with a regular insulator. So the first time we were experimentally able to show this is now 14 years ago, and a study led by my then PhD student Asif Islam Khan, who is now a professor at Georgia Tech. So what his work showed us is that yes, you can put 2 capacitors in series and you can increase the capacitance rather than decreasing it. And we were, of course, all these years we have been very focused on transistors, but we essentially said that if you can enhance the capacitance in this way, this is an unconventional increase in capacitance. So anywhere you need a larger capacitance, you can use it. For example, in DRAM, for memory, for example, in energy storage at the back end. At that time, we did not know that this will become very important for backside power delivery, which is becoming the name of the game for today's transistors. But yes, even then we needed back-end capacitors, and we said that we should be able to use it. So over the years, we kept, this is, what happens is that whenever you come up with an idea that goes in the other direction of a textbook, usually people come and say, you must be wrong. And so we have had many discussions with people who said, you are wrong. And I say, okay, explain to me how I'm wrong. And they'll say, I don't know how you are wrong, but you must be wrong. So, so over the years, it took us a lot of experiments and studies to kind of establish that, no, this works, and we can get it to you in a way that you can actually use it. So one of the examples I'm showing here is that it's based on a material called hafnium dioxide, which we already use in our transistors. And in the hafnium dioxide, we are able to actually stabilize a ferroelectric phase, and by that we are able to get a negative capacitance. So we are able to stabilize the material where that middle part is. And there is a very, you can image it, and what you can see is in this stabilization, you have polarization like this pointing up, polarization like this pointing down. So in the middle, the material does not know which direction to go, because on the left, somebody is trying to put it up, on the right, somebody is trying to push it down. So in the middle, the region, we call that a frustrated region, because the middle region does not know where to go. So in that frustrated region, then the material stores energy. If you think about it, it actually makes intuitive sense. If somebody is stretching something up, somebody is stretching something down, then in the middle, you will store energy. And that energy then resembles that little hill in the middle that gives us negative capacitance. So that allows us to do something very remarkable. So what I'm showing here is some results where we put hafnium dioxide, which has a permittivity of around 19, and zirconium dioxide, which has a permittivity of around 40. But when we put them together and stabilize them in the in this negative capacitance state, it gives us a permittivity of 52. This, again, it goes beyond what the textbook, standard textbook says. Because if you are trying to increase the permittivity of a composite material, you are never going to introduce a lower permittivity material, right? You want to introduce, but what happened is that when we put a lower permittivity hafnium dioxide into zirconium dioxide, the total permittivity went up. And there is a reason that we did it, is because hafnium dioxide is used everywhere in our industry. Okay. So what happened is, this started getting used back in 2020. We were, of course, not aware of it, because when industries adopt something from the university, and I wanted to emphasize that because that's how it goes actually. When the industries adopt something from the university, they do not necessarily tell the university that we have done something that is inspired by your work. So this was done in 2020, Samsung 1Z DRAM. In 2023, there's a company called Tech Insights. All our industry colleagues have subscriptions to it. We at the universities cannot afford to do that. I wanted to mention that because often I hear from Bangladesh that, oh, we don't have money to do this and do that. Even in the US, we say that Berkeley is essentially rank 1 in whatever we do. Even we don't have the money to do all kinds of stuff. So what Tech Insights did is, Tech Insights, this company often publishes some of their results. They sell their subscription to industries, but every 2-3 years they will publish for free. So from their result, we got to know that Samsung is using it. But it has an interesting history. Before we knew that Samsung was using it, Tech Insights actually published the back-end MIM capacitor result of Intel. So Intel also commercialized in 2020 something they call Super MIM, and in 2023 from Tech Insights results, I saw that that material looks exactly like our material. So then there was a workshop at Berkeley, and I was showing this, and in the audience we had Intel's, we had Samsung, Applied Materials, Lam, all the big company representatives. After I gave the talk, one of my former students, who is a VP at Samsung now, he came up to me and he said, "Professor, you should look at our DRAM." So we looked at Samsung's 1Z DRAM and we found that they're also using it. So after this, in December 2023, I bought an Apple MacBook, and I also bought my cell phone here because both of these uses Samsung 1Z DRAM. And so it is a lot of satisfaction for a university faculty to know that the material that we basically worked on in our lab is being used in a real product. Anyway, so coming back to transistors, what we can show now is that in a transistor gate stack that looks exactly like advanced gate stacks, we can actually get larger capacitance than what is reported by industries. Okay, so you can see this orange curve is from Berkeley, what we call Berkeley NCFET. The capacitance is much larger than what is the control hafnium dioxide. This is published actually by Intel on their transistor. So our capacitance is much higher, although the physical thickness is similar. And because our capacitance is much higher, as I said, that capacitance is dQ/dV, so you can switch a lot more charge at a given voltage, or you can switch the same amount of charge at a smaller voltage. So I'm showing some results on done on our transistors, the transistors that we built at Berkeley, and this is compared with a TSMC transistor that is of the same length. So nothing to dish TSMC about. This is what we found in published results, so we could only compare with that. And what you can see is that we can get larger on current and lower off current at the same voltage than TSMC's commercial transistors, even in a transistor made at a university lab. We can do that because our charge is way higher than what the advanced industry stacks had at that time. As far as I know, the most advanced gate stacks we heard about 3 nanometer, 2 nanometer. Those are mostly for TSMC node numbers. they're now using zirconium as well. But I don't have access to tech insights. Hopefully in 2-3 years, I'll be able to show you that is data stack as well. But as far as I've been told, this is already being used. Okay, so now the question is, what does that give me? The fact that capacitance is going up, capacitance in our field often is parameterized by a thickness. So lower the thickness, higher the capacitance. We often call that effective oxide thickness. So when I showed you the result, let's see. The advanced gate stacks effective oxide thickness are around 9.5 angstrom. Ours is 6.5 angstrom. So that's the larger capacitance. In our lab at Berkeley, now we can get down to below 5 angstrom EOT. We are around 3 angstrom EOT or so. And if you look at how much VDD scaling is possible, that already allows us to go down below 400 millivolts. So I am now basically setting a target for our group that we will go down to 0 angstrom EOT, a thickness of 0 angstrom or even negative. It is actually physically possible. So that's our next goal. But if we can go down to that level, TCAD shows us that we should be able to go down to 300 millivolt. So that's the target right now, because you can ask why not 200? That's for all the young people here. It's not 200 yet for me is because of the noise. If you remember that we said that we are now building chips with 200 billion transistors. It will become 1 trillion in the next 4-5 years. Okay, so when you have 1E12 transistors, your error immunity has to be 1/1E12. Okay, and usually because of the short noise in circuits, we get 5-6 millivolt of noise. So if you are only working with 300 millivolt of operating voltage, you can show that your error immunity is only e raised to -6, which is actually not good enough. You have to go to 1E-12. So there may be ways to work around it, but that's what we are targeting, that we want to go down to 300 millivolt. That reduces the energy dissipation out of the door by 10x. If we then bring in system level innovations that can go to around 1000x, that will be significant change in terms of the challenges that I posed in the beginning. Okay, if your electricity bill is $40 billion a year, that goes down to $4 billion because your energy dissipation is 10x lower, it immediately makes it much simpler. If it can go down even more, it will make it even simpler. So that's our goal now, and we think that we can get there. All right. So with that, I'm going to conclude my talk. That's a snippet of the kind of work that we have been doing in our group. Hopefully that provides an example of exploratory semiconductor research that happens in the US. But one of the things that I mentioned, that this symposium is of course not about research work, and as I said that I'm out of my depth here in terms of talking about semiconductor workforce development and others. But there are a few things that I have learned through my experience in the US, and that's what I'm going to talk about here, which is that typically we talk about a curve like this. Any market in the semiconductor side has to have an exponential growth, and once the exponential growth happens, we say that is a market. So industries go there and they try to ride that wave. So US funding agencies will always say that I can only give you money to do research if you can change the scaling of that exponential growth. They will say that if something is in the market, like let's say that microchip, it's already in the market, that means the companies have figured out that they have an exponential growth model, otherwise they would not be there. And those guys have so much money, they are able to ride that wave. They will be they will be following that path. So I'm not going to spend money on that. I'm only going to spend money if you show me that you have a way of changing the scaling of that path. So that's what, as academics, we have to make. That is the argument we have to make to the US government, to say, give us money. And not only to the government, 50% of my research funding actually comes from the semiconductor industry. And they will also tell us the same thing. They will say, yeah, if you are simply doing a scaling of silicon transistors, I'm not interested. I have 3,000 engineers who will do it for me. You go and figure out what is the new thing that you can do. So that is very important. But most of the time, that new scaling curve will have a ramp up period. You see that intersection point, right? Before that, that new curve will always fall behind the state of the art. And that's where government usually says that that's what I will fund you for. Once you cross that intersection point, now the market will pick it up. That's the funding model. So as we think about how we do that in Bangladesh, there is something to learn from the US model itself. It may not have to be the same, but these are some of the lessons that we have learned. So a few takeaway points for me. I feel that leading academic institutions like BUET, like Dhaka University, where the cream of the crop students go, they probably should be enabled to do fundamental science and fundamental engineering. What I mean by that is that these kids are probably not going to be heavily excited about trying to go for jobs that are routine jobs. You can probably recruit them, but it will be hard to retain them. That's the lessons that we have learned in the US. So if you think about today, US Semiconductor Workforce Development Initiative, a lot of that is actually focused on community college students, not on the top graduate college students. So definitely, the top institutions will have to start it, but then it has to go to the other other educational institutions. Because my thinking is that the people who are heavily intellectually engaged would like to actually ride on that new scaling curve and not just directly run into that conventional scaling. So that's one of the things. What we also have learned is extreme science or extreme engineering. Both are very useful, but not in between. So if you think about, let's say we have applied materials here, but if you think about what they are doing, this is mind-boggling. They are etching 100:1 aspect ratio. If you think about that, that's like 30 nanometer gap with 3 micron length. So if you are trying to etch something or deposit something in it, if you just think about it, you have to have your precursor gas molecule to fit in that hole and go all the way and deposit and also come out, right? How do you do that? So essentially, they don't do it in the gas phase. There is a chemi-absorption. So the gas goes in there, it becomes a liquid, then it flows into the bottom and is able to deposit materials. This is extreme science. And creating that hole that is just 30 nanometer in footprint and 3 micron in depth is extreme engineering. But if you say that I'm going to do that in a plane, just I take a wafer and deposit some materials on it, that is in between, that's not useful. So that's one of the things that one needs to be careful about. If you look at Asia and we look at history, all the Asian superpowers in semiconductors, they all had a key local market. I do not think that we can be very successful if all our effort is based on contributing to the products which are going globally. If you look at how Korea started, their KAIST started to support their military. If you're looking at what India is doing today, the entire government funding, almost 90% of it, is actually supporting whatever technology will go into their military. Okay? If you look at China, China is getting blocked out from the global semiconductor market, but their entire semiconductor research and semiconductor development is for their local market and then exporting, right? So I think finding local market is a key, and this needs to be discussed. It cannot be just that we contribute to the global market. The other thing, the last point I'll make is the common good model. So in the university, in the US, they talk about for government funding, they talk about the common good model. They try to figure out what is useful for everyone. Okay, and they try to fund that, and then what they do is they basically say that we will try to enable the market, and part of that enabling comes through all kinds of incentives for industries. So this is another thing that has worked very well for the US, and something, again, as I'm saying, that Bangladesh is different, the realities are different, so it doesn't have to be that exact same model, but because these models have been successful in the US, something to keep in mind and learn from. So on that point, I'll stop. Thank you. I'm happy to take any questions if there's time. Otherwise, yeah.
Data center market. I'm wondering, given the implications for energy consumption, have you been able to have support from the energy infrastructure companies for the research that you're doing?
So I would say that my supporters are mostly all semiconductor companies. Yeah, so that's what we have been working with. There has been some interest from companies who want to build supercapacitors. We are interested, but we are not a group who work on that side, so we have been on the fence whether we should jump into that or not. But mostly my funders are all semiconductor.
My name is Abdullah. I'm in visiting professor in NSU now, from New York City, University of New York. I spent 16 years here actually in Bangladesh, in between my last 50 years life in the USA. What I wanted is very encouraging, what you have presented, fantastic research work, decreasing the energy efficiency. But looking at Bangladesh, have you thought about, since you are here with all of us Bangladeshis, any kind of fundamental research is not very practical here. Funding, research, students, any leapfrog, the overall concept that if we can do something that overall, we don't have a data center also in this country yet, our own, not strongly. So that issue of consumption of data center power is not much there. But leapfrogging, have you thought that if Bangladesh talents, they could do something that not but fundamental, but some kind of applied level in connection with your UC Berkeley, that our different groups could do, so that we could have some initial outsourcing potential and probably later on into the Bangladesh's economy. Have you thought about it?
So I have been part of many discussions that go in that direction often. I'd say that we have not found a good model so far. And one of the main things there is that applied research often comes with these IP restrictions. So how do we handle that if we are doing something with UC Berkeley and Bangladesh, who owns the IP, will become a very difficult problem. And in fact, we have just heard about creating an industry makers space this morning. I would say that when you are going to implement that, you'll find that implementing is very hard because of industry is getting very worried about their IP contamination. How can you work in a common space and not contaminate your IP? So I would say that it's a very good thought. I have been part of a number of discussions with various Bangladeshi teams over the years, but we have not found a good model. Fundamental research, on the other hand, is different because that's open and you can collaborate as much as you want. So there are some hands on the back as well, sir.
You have actually pictured a very dire future in terms of energy consumption of computation, but that's based on the charge-based electronics, right? What do you see are the possibilities of change in this paradigm, like a quantum computing, spin? If something else comes, how will this situation change, in your opinion?
So that is a loaded question. The first thing I'll say that I did not want to paint a dire picture. Any challenge actually brings in more excitement. You want to be in a time when you have a grand challenge. I would say that I have seen this field for 25 years now, and I'd say that every year it is becoming more exciting, because when I was doing my PhD, there was an idea that, oh, we still have 15 years to go where we can just scale down the transistors. That comfort level is going away slowly. It's becoming more and more expensive to do that thing. So people are starting to think more in, often they call this functional augmentation. So things are getting more exciting. I would say that this is the best time to be in this field and think about new things, because there is a real chance that those new things will make some impact. Now, for the other part of the question, I have been thinking about, so quantum is a very different thing. I am not a big believer that quantum is going to change much. Quantum may change a few things, but so far we have not been as a community, and I talk to my colleagues on the quantum computing side all the time, and they will agree with me, is that we have not found a generic use of quantum computing. So yes, for certain things, if they are successful, quantum computing will allow us new capabilities, but as a general purpose computer, we don't yet see that. Changing the state variable itself from charge to something else, right now, my understanding is that it's probably not going to do much, simply because, again, in the fundamental sense, you cannot switch the to state of any state variable violating the second law of thermodynamics. And the charge-based electronics is very close to that limit. So there's not a lot of space for something new to come and completely change something.
Thank you very much. Wonderful talk. I have a two-part question. Question one would be the limitation on the millivolt you mentioned is 300 because of the error margin. Is the error margin limitation primarily due to the material itself, or is it due to the fabrication model? For example, you can't go thinner than certain...
So it's actually very, very fundamental in the sense that it is a short noise problem. The short noise is there in any RC circuits, and that comes from fluctuation dissipation. So you have temperature, and temperature, if you have any conductor, so because of thermal noise, electrons are doing this, that gives you some noise. And in our circuits, if you measure a circuit, we see that's of the order of 5 millivolt to 6 millivolt.
So it's more a physics-based issue. Okay.
Yeah.
The second part question would be probably even connecting Bangladesh to it. So your primary focus is on the device. You're trying to see how you can manage the device power performance. Is there any focus on the system level, for example, both at the CPU level, at the memory level, or the combination of system itself? Like, Tesla has to have this the Dojo chip. So is there something, and I feel it's difficult for new economies to beat US or even advanced economies in this device because it's been done for 40 years. It's going in that curve. For them to beat the curve, can they start looking at, or like you mentioned, leapfrogging into system level and say, hey, we can look at new solutions for system level integration and try to improve it?
I'm going to say that definitely, but I'm also going to say that all industries are looking heavily into system level optimization to reduce power dissipation. So you have to figure out how you can contribute to that. But of course, I mean, there's no reason to focus on only one specific area. Yeah, so I think Professor Hussain is indicating that I have hugely overstayed my welcome. So, so thank you very much. And if you have other questions, I'm available. I'll be very happy to discuss with you. Thank you again. Thanks.
Thank you very much, Professor Saif Salahuddin, for your wonderful presentation. Now we are moving forward for the next session. Before moving forward to the next session, I would like to request my team to prepare our stage for the next session, and